Okay, the species that we selected here, it's called Linx pardinus. Yeah. To download this data, we are going to use the GB function in the Dismo package. So Linx pardinus. Before downloading the data, you can use download equal false and run this function to find out whether there is any record or not. So it just returns the number of observation available in GBIF. Now I know that there is some records, and then I can change it to true. If I use geo equal true, it just return the records that has geographic locations, geographic coordinates. And if I use sp equal true, it returns, it convert the data into a spatial points data frame. But for this case, I just download the record as a data frame. So this class of this sp, if I check it, it's a data frame. And if I check the name of the column, you see I put $sign here and I get a list of all the columns. There are a lot of columns, a lot of data available here. But for my case, actually, I just need the columns that specify coordinates. It's called longitude and latitude. I'm going to use them, but I know that most of the times I have some missing data in those columns. And when you have missing data, you usually get NA, capital N, capital A. I don't know if you use that. That is just null in R. So I'm going to find out which records actually is NA, is missing, by trying the NA function. Is NA? So I use sp $sign lon. It means that check whether it's an A, check which record, check whether each record is an A or not in this column. And if I put which here, it simply returns which record is an A. So now I have the numbers, that the number of records or the row numbers in the data frame that are an A. I can put it into an object like W, and then I can simply remove them by using -W here. So I say just remove these rows, -W, minus these values. I remove them. I can do the same for latitude, but usually when I remove those missing, I don't get anything here. So there is no more missing data. And now I'm going to remove the additional column in the SP object. So first, let's add a new column like a species. I make every value in that column 1, and then I need to keep longitude and latitude here as well. Let's run it again. So now I have 3 columns, longitude, latitude, and species. I remove the other columns. And to convert this data frame into a spatial points data frame, I can simply use the coordinates function. When you use coordinates, you're going to introduce the name of the columns that has the coordinates information as a formula with only the right-hand side. you need to specify tilde sign, and then the name of the longitude and latitude column. And now if I check the class of SP, it's not data frame anymore. It's a spatial points data frame. I can check the head of the attribute table to make sure if we have only one column. Yes, it's only one. So now I have presence only data. The species data is downloaded. Let's download the predictor variables. For the predictor variables, I'm going to use get data function in the raster package. I use word clean, the same as what we did yesterday. The variables bioclim and the resolution, which is 10 minutes. So the variables are downloaded here, 19 bioclim variables, and then we are going to check the collinearity structure. We are going to use the USDM package, and in USDM package we have two functions, VIF step and VIF core. You can either directly put raster values, raster object here, bio, or you can put a data frame. If I want to put a data frame, probably I need to extract the raster values in the species location. Usually it's a better approach if you have enough sample size in your species data, because those locations are the one that you use in the model. But if you have a lot of data over your study area, you can simply use your predictor variables here. So the question was that what is the difference between VIF step and VIF core? I simply try both of them. And VIF core, actually, you should know that the default threshold is 0.9. You remember VIF core actually first test pairwise correlation and then remove, if it is greater than this threshold, it removes the one with greatest VIF. So the default is 0.9, but we can change it to, for example, 0.7. Let's try this one as well, and then check the result for both. So in VIF step, actually, it is suggested that we remove 10 variables. In the second one, it is suggested that we remove also 12 variables here. So then you can compare actually which one are suggested by both. One approach is probably to just remove those that are suggested by both function, or you can just simply use one of them. Let's here use the second one. It's up to you, but let's use the second one, V2, and then make it like bio M. So now this bio M has 7 variables. We have species data, we have environmental variables that we also check for multicollinearity. Now we just use 7 environmental variables to fit the model. Before starting the modeling, I'm going to plot the species data and the variables to see the distribution. This is one of the variables here. and this is a species data. So all are located here. Probably I should use something like this. So it's I think it's over Spain and Portugal. If I use map view and put here, you see when if I check, I think it's interesting to know, if I check the projection of my SP object, it's NA, it's not defined. That's why here I don't get the background map. But I know that it is a geographical coordinate, so I can define it. If I know what the definition, I can define it here. Or it's a trick here. I use projection function to extract the projection value from a raster, and the raster would be an empty raster I create by raster function. So this raster function create an empty raster with this projection, and I get the projection from this empty raster, which would be the projection that I want to define for this one. So if I use this one and run it again, it would be over the area that I want. Questions? This actually check the projection of the spatial object, and it here before I assigned the projection, it was an A, right? Because we simply used this coordinate columns. When we download data, we use the coordinate column to create this spatial points object, but we didn't define that projection. The object doesn't know what is the projection, but we already know that it is a geographical coordinate system. So I just wanted to specify the coordinate system, but a trick to specify this definition is like, first I create an empty raster and read the projection from that empty raster, which is the one that I wanted, and then I assigned as a projection for this SP object.
No, it's all good.
Okay. So now everything is ready to fit the model. I load the package STM. You already know how to install the package, the latest version, and also make sure you run install all to install all the dependent package, all the packages that are required by the different methods. When you do that, you are going to first use STM data to create the STM data object. Here, first you check the name of a species, which is a species here. When in such a case that you have a spatial data like a spatial point raster predictor, make sure that you only have the species data in your spatial points. If there are some additional column, it is likely that they are wrongly get as a predictor, specifically when you don't need them. So here I'm going to specify a species against everything else. Just specify a formula, and then my training would be SP, and predictors would be this bio M, right? If I run this one, The data is generated, but look at here. It is a presence-only data. But most of the method that I'm going to use require presence-absence data. And since it's a presence-only data, I need to generate pseudo-absence. To do that, I can simply use bg argument here that generates background data. I can specify the setting here, like the number of pseudo-absences. Let's try 1,000 pseudo-absences here. So we have 1,330 locations. But if I check the original number of presence data, it was 500 something. And then I generate 1,000 pseudo absence. So I should have 1,584. But why I have 1,330? What happens to those 200 points? Probably there were some duplications, and they are automatically checked, and if there is any duplication or missing value, they are removed. That's why we get different values here. The data is ready. We can use the SDM function to fit the model. Again, we can specify the formula here. We are going to specify the data object here. And then we are going to specify some methods, different algorithms. Yes?
Is there a way to fit all the methods in one go except for typing them all out? Because I don't really know which method is really better than the other one.
You can simply put the name of all the methods. You need to get the names here. So you can just put all the names. Yeah. But probably in future I will add a function like all, then it considers all. But now it's not available. So I'm going to try several of them. Okay, I think it's enough now. And then we are going to use a let's put it in the second row, replication technique to partition them. Let's try bootstrapping. And then if you use bootstrapping, you're going to specify how many runs you want. For this case, I just need 2. But you in real case, you may use like 100 or even more or less, 30 times. Depend on the size of data and the times that are required for it. And let's fit the models. I think it is for assignment 3. And now if you just get a report here, you see how many methods are selected, the success rate, and the summary report. It's an average over all. If you have several runs or several replication, then it's an average over all the runs that you have here. So you see it's perfectly fitted. But one thing you should consider here, sometimes it's not the real value because you didn't have true presence and absence. You use pseudo absence to evaluate your result as well. And since you had a lot of pseudo absence, that's why you have huge inflation in your estimated accuracy. So keep in mind that usually it's better if you have real pseudo absence to evaluate your model.
For the pseudo absence, do you have different methods to generate, or just a random way?
Okay, it's a good point. Actually, there are different techniques to generate pseudo absences, but I believe that the most correct one in the state of the art methods is the one that randomly selected over the study area. That's why there are some other argument here like method equal, and now the default is G random, means randomly distributed over geographical area. But I'm working on a new method, a new concept for generating the pseudo absence. It would be called e-random, which is randomly generated method over the environmental space, not geographical space. So it's it needs some conceptual discussion, but let's don't go through them. Just know that there are different methods, and the most correct one based on the current state of the art would be this one. Now the model is okay. We are going to predict. We use predict function. Then we use the model. And as the second argument, we simply use the raster data, which is bio m or bio, doesn't matter, bio m. And then a file name in which the data is saved in your working directory. Let's make it like predictions dot. Then the extension would be the format. Let's make it as img. You can add, for example, mean equal true. It means that if you have several runs for each replication, for example, we have here in the method, we have 2 runs for each model and each replication. Then if you put mean equal true, you're going to have the average over all runs for each technique. But if you leave it empty or mean equal false, then you get an individual prediction for each run, each technique. So let's try it. When it's running, let's try the ensemble function as well, which would be the same. But for ensemble, actually, we need to specify some setting. First, we need to specify what ensemble method should be used. Now, 2 methods are implemented in the package. One is unweighted, means just take an average over all the methods. Another one is weighted. Weighted means weighted average, and it actually gives more weight, higher weight to the methods that have higher accuracy. When you use weighted average, you are going to specify what statistic you are going to use, whether the weight is generated based on, let's put it here, AUC or TSS or sensitivity. There are different statistics, right? Let's first, before explaining this, let's look at the output of the model here by GUI. I think it would be useful. In the first page, you get the same report as you generated in the main console, but here you get a table including the details for each run. So in total, we had 10 models. This model ID is very important because if you want to take the result for a specific model, you're going to use this model ID. So here you can simply know that, for example, model ID equals 6 would be a random forest generated based on bootstrapping replication, and the second run, we had 2 runs, right? And this evaluation parse actually generates some plots here. So we have, we could have several species, but here we have one species. So we get the results here, but we can select, okay, if you just need the result for GLM, you can select it here, GLM and random forest. So it's interactive, and you can select the method here. You see, it's an easy way to look at the result. You have the graph based on both training data and test data. Usually test data would be trustable result. There are the other plots like calibration plots. I'm not going to explain the details about this plot. It needs some time, but it's something relevant to evaluation of your model. So you get this plot for each individual model. And this plot actually is threshold optimizations. You remember I explained that there are different ways to show for it to find the best threshold. For example, the threshold that maximizes TSS would be 0.68. If we want to convert the probability into presence and absence, we're going to use this threshold based on 0.68. Means probability greater than 0.68 would be presence, and less than 0.68 would be absence. But we can use the other statistic as well. Max the kappa statistic, or phi, or so there are different ways, and for different models, you see. So you can explore the results. We have also density plot. You remember the discrimination between presence and absence. You see, they are highly discriminated, presence and absence. For all absence, you have low probability of occurrence, and for all presence, you have high probability of occurrence. And you can get for all the models here. It's just strongly overfitted. The same for boxplot. Boxplot also show that information in different ways. And this one also is very important. For each model, you see different statistics like TSS, specificity, sensitivity for different thresholds. These thresholds are the optimized threshold based on different criteria. This is the criterion that specificity is equal sensitivity. So under this condition, the best threshold will be 0.7. Under this condition would be 0.68. And you have different criteria. So in different parts of the package, you may be asked, for example, in the ensemble, when you want to specify the statistic for weighted averaging, if you specify TSS is a threshold dependent. Then you need to specify based on which optimization criteria you're gonna find the threshold to calculate TSS. And you just simply specify 1, 2, 3. That refers to these row numbers. That is different criteria. Usually this second one is the widely used technique. But we have some threshold independent values like AUC, correlation, deviance, calibration, prevalence for different methods, different models. So you get the values the same. This tab also is very important for interpretation. For each model, you get a graph that shows the importance of each variable. Here you see bio 9 for this GLM, the first run of GLM is very important. Let's check to see whether it's the same for the second run. And then for S support vector machine. So it shows variable importance for each method. You see we have differences for based on boosted regression tree. Bio 18 is the most important variable. Based on random forest, bio 19. Based on a GLM, bio 9, for example. So it's relative importance of each variable, and it's very good for interpretation. So here, when we specify AUC, since AUC is a threshold independent, it's okay. But if we use TSS, we're going to add another argument, which is optimization method. For example, if we put 2, it means that the second row in that table that I showed. So let's run this one. So now we have P here out of the predict function, which has 10 raster layers inside because we had 10 models in the M object. Here we would have 10 variables, 10 rasters, all probability of occurrence corresponding to. Now, while it's running, let's also go through the one that's explained about future projection in future. When you want to project for future, because this raster map would be the probability of occurrence for the current time, but for future time you need the variables, the bioclim variables for the future time, and to download them you can simply use again the get data function. And if you check the help page of the get data function, here in the last part, you can see the setting for the get it. So this, instead of WorldClim, you're gonna use CMIP5. So you just simply use this one as the name of data set, and the var you use is the same bio. And then you need to specify resolution again, which would be 10, and RCP scenario would be 85, year would be 2070, and the last one would be the model, but the GCMs, the climate models. The model would be either of them, but let's try the first one. Then let's put it in BioF.
It'll be just 70 instead of 2070.
Probably, I don't, yeah, it should be 70. So the year should be 70 here. let's take a look at this result here. We have P, which is a probability of occurrence for 10 models, and if we plot them, you get the result for different methods, right? This is for the first model, like the fifth model. So you can also specify like 1, 3, 5, 7, 9. From each approach, I just took one of them. Let's compare them. So you can see there are different patterns, and you see the green color here, the distribution. I'm going to make a trick here to get my ensemble, just simply by taking mean over all the layers, but you're gonna use this one. So this plot would be the final ensemble. Just imagine this is the final ensemble. So this is the final ensemble map, okay, for the current time. And now I downloaded bioclim data, the same bioclim data for future. We have 19 bioclim variables. But there is one thing. When you download bioclim data, when you check the names of the variable, you see the name is different. It's not bio1, bio2, bio3 anymore. If you put this layer into the predict function, you get the error because the name of the variable is not the same. If I check the name of original bio we downloaded, is bio1, bio2 till bio19. You can simply assign these names to this new object because the order is the same, 0, 1, 0, 2 until 0, 19. The order is the same. That's why you can simply say assign the names of bio to biof. And now this biof has the same name as the origin, the bioclim in the current time. And then we are going to simply use the predict function, the same as what we did here, but for the future time. I put it here, predictions f. And for ensemble also you can use this one, the same. And here you put biof and then a new name. The same actually, but just with the future climatic data. And then you get the pattern for future. I use this unweighted. This is a function for unweighted average, unweighted mean. It's for raster package. It's this unweighted average is quick. That's why, since on my machine it's not, it takes time. That's why I'm using this one instead of this one. But you have the code here to use the weighted average. So this one is done now. Let's generate ensemble as well. Then I'm going to make a stack of EN and ENF, which is the current and future, to compare them. This is the current time, and this is the future time. Ensemble output for the current time and the future time. Yes.
So, in the worst case scenario, the possible distribution of the links is increased. Okay.
Yeah, but it goes northward. You see. So probably it's good to better focus on, for example, let's plot on the future distribution and then look at the patterns here. Or we can simply use a map view function to compare them. So when you use a stack, we use a stack of the current raster, the probability for the current time and the future time. And here we get both layer here. So this is for the current time, and this is for the future time, you see. So they shift to northward. Yes.
If you zoom out, was it also present in America in the future? Because
Sorry?
if you zoom the map out, yeah, why is it suddenly in America?
Okay. We just simply link the conditions, environmental conditions, to the environmental conditions. We characterize the conditions that the species are observed, and it maps over the world which other area has similar conditions. So apparently this area has suitable conditions, so we can see. So you see the effect of climate change, huh? So the next question was, calculate the changes between the maps. Yes. So to calculate the changes, we can simply calculate the difference in probability. We have ENF, and for future, we can simply say ENF minus EN. And then we can make it like CH. And if I plot it, I get a raster with some minus and plus value. So this plus value are those that gain suitability, and this minus are those that lost suitability. You see? And a lot of area is 0, means they are the same. They didn't. So you can find the changes, right? Clear? Or we can convert the maps into probability of occurrence, into the maps of probability of occurrence to presence and absence. To do that, we need a threshold. The question is that which threshold we should use. If we take a look at the result, there is a function called get evaluation. We can simply get all the evaluation metric in a table, in a data frame. Or if you remember, in this GUI here, we had this tab here that shows different threshold for each model. Different threshold based on different criteria. So if, for example, if we consider this criteria, the second optimization criteria, and then look at the threshold, but we have different threshold for different models, right? We can ask this get evaluation function to get the statistic that we want, the statistic like AUC, for example, this generates AUC for all the 10 models. For here, we may say, okay, I want AUC, TSS, and threshold. But if I specify some threshold dependent value, I need to specify also which optimization threshold should be used. The second one, for example. You see here, I get all the statistic I specified here in a data frame for all the model IDs. And this is the threshold is used for different. Since I use an ensemble that is an average over all the methods, I should either use the one that has been frequently specified, or I can take an average over this column. If I put it in this object EV, and then I can say mean of EV $ threshold, then that would be the threshold I can use to convert the ensemble to a presence and absence. To do that, we have EN and ENF, right? To do that, we can use if-else function. In if-else function, you can say, let's check the values inside. When you put a square bracket in, you refer to the values of the inside this raster layers. If the values is greater than or equal of this value, there would be 1, otherwise there would be 0. And the result would be into PA, for example. First, you need to generate a raster, an empty raster based on EN, and then you just assign, you just use it like this. So you just check the values inside EN to see whether it's greater than this threshold. If it is greater than or equal of this threshold, then it should be 1. Otherwise, it should be 0. And the result would be into the corresponding cell in PA. We already created PA as an empty raster. So when you use raster and put another raster here, it creates an empty raster based on the raster you specified here. So this PA is an empty raster with the exact definition as EN. And then if I run this one, PA would be the presence absence pattern for the current time. So the presence absence would be here, the distribution. And we can do the same for the future time. I make P and F, PAF, E and F. So you see that this is the pattern for future time. Future time, current time, you see? And then, again, we can compare these two together. PAF minus PA would be PAC, for example. If I plot them, I get 3 possible values: 1, 0, minus 1. 1 is when in the it was future minus current. If in the future time it's 1 and in the current time it's 0, it means gaining, it's colonization, right? If in current time it's 0, but it's future time it's 1, it means the species moved there, it would be 1. If in the current time is 0, in the future time also is 0, then it would be 0. If in the future time is 0, but in the current time is 1, it means extinction. It's -1, right? So these three values are interpretable, and I can actually specify a color palette here, like CL is color ramp palette, and specify the color. For example, for extinction, I can use red. For persistence, I can use white. And for colonization, I can use dark green. And then for color, I can use 3 levels of this. Let's make it gray. So you see, I just simply generated 3 classes: extinction, persistence, and colonization. So here we actually generate extinction and colonization. Okay? Clear? Interesting?
Just shortly scroll a little bit more up. Yes.
Could you make the dark green, could you make it blue?
Yeah.
Colorblind, so you can see it.
This one?
Yeah.
Dark blue or just blue?
Doesn't matter.
Or you can make it blue. Or you can make it gray, lighter gray. Yes? Any question? Okay, I think we covered everything, right? Is there? Oh, okay. There is one more thing you can generate based on the result of the. Let's make it additional. That's additional. I don't know. Note. Which is response curve. Actually, we can generate the response of a species to each variable. That would be really useful for interpretation. In the latest version of the STM package, there is a function called rcurve. When you have rcurve, you just simply put the model object here, and then you get a plot that would be response curve. So it shows probability. Here we have the environmental variables, and it shows the species response to environmental variables. You see, for bio 9, within this range of the bio 9 variable, you have the probability for that species increased. And here, so you're going to find out the range over which your species can survive, something like this. And you can generate the same plot for so here you have other argument like ID, for example. If you put 2, it means you generate the same plot for the second one. If you put, for example, 9, it's completely other approach.
What's on the x-axis?
Each corresponding to each variable is bio 2, bio 8. So it's the values of bio 2. Different values of bio 2, different values of bio 8, and its probability of occurrence. So that is called response curve. Is it clear? It's very important for interpreting the results.
So in this case, bio 2 does nothing?
Yeah, in bio 1 and bio 2 for this technique actually shows nothing. If I compare this, for example, this was for the ninth model. If I compare it with variable importance, var let's see. Okay, get very important. If I use m and take the variable importance for the ninth the ninth model and plot it, so it was first one, it was bio 9 the most important, and bio 19 and bio 18 was not important. And here in the result also you see for bio 9 and bio 8, if you compare it here, bio 9 and bio 8 were the most important variable, and for bio 19 and bio 18 it's nothing. Here also you see there is no importance for them. So these two, response curve and variable importance, are two ways to understand the relationship of between environment and species distribution to interpret the result.